Hi everyone, this is the first video of the Generalized Linear Model series. Generalized linear models are an extension of classical linear models. So it's a very good starting point for us to do a recap on the classical linear models. Usually we write a linear regression as the following. So we have y equal to x1 beta 1 plus x2 beta 2 all the way to xp beta p plus epsilon. There are a few assumptions in this way of writing the model. First of all, we assume that imagine we have I equal to 1 to capital N observations in our samples. So we know that epsilon I follows normal distribution or Gaussian distribution with mean zero variance sigma square. That's one assumption we have. And because of the normal distribution of the error, we can naturally get that the expectation of y is equal to expectation of the x times beta part plus the expectation of the epsilon. And as we said, because epsilon is a normal distribution, epsilon follows a normal distribution with mean zero and variance sigma square, this part is naturally zero. And as you will see later, this is what we call a systematic component, meaning that these beta can be estimated from the data, and the x are the observed values. So there are no random part, which means we can drop this expectation. So what we get here is EY is equal to XI transpose beta. Or if we write it in a matrix form, then it's X beta. It's very important for you to recognize this step because the generalized linear model extends this way of expressing a classical linear model. Sometimes we put I in the footnote. That just means for each individual yi, it follows normal distribution with mu I and sigma square. Notice the sigma itself has no footnote. So all the individuals share the same variance. That's what we call constant variance. Okay, so it's more straightforward to think of epsilon I as the random part. However, epsilon directly determines y, so that's why we refer yi as the random component, in contrast with the systematic component. As the title suggested, there are three components in generalized linear model framework. And we mentioned the first one is the systematic component, then we have the random component, and the third component is a link function. Link function, as the name suggested, it connects the random part with the systematic part because that's the only two components we've talked about. So it connects, specifically it connects the mean of the random part, random component. In other words, the expectation of yi, which is mu I, with the systematic part. So that is, we can write it as xi beta I. And let's use this eta to denote the systematic component. So the link function, usually we use g. g of mu I is equal to eta I. That's how we connect the systematic component with the random component. In the classical linear model, the link function is actually just mu I itself, so g mu I is equal to mu I. It's very simple. Okay, now we have the three components identified in the classical linear model. Let's move on to its extension, the generalized linear model. So, what are exactly the extensions? First, in the classical linear model, we assume that yi follows a normal distribution. However, in generalized linear model, the response y1 to yn, they're assumed to share the same distribution from the exponential family instead of normal distribution. And normal distributions is actually a special case of exponential family. I have another video that goes into details of what exponential families are, but basically any distribution of the form exp yi bi theta I plus ci theta I plus di yi. Any distribution of the following form are exponential family. Some examples include normal, of course, and binomial distribution, Poisson distribution, and so on and so forth. So these are some of the examples. All right, that's the first distinction between generalized linear model and classical linear model. The first part is called the random component. And the second part, which is the systematic component, it's actually the same as the systematic component in classical linear model. So we have xi transpose beta, or you can write it as x beta, depending on how you define your x. So x is actually x1 transpose all the way to xn transpose. And sometimes if we include intercept, the first column of x, the design matrix will be O1, and then the rest are the observed x values. All right, that's a systematic component. And then the link function, it's a monotone differentiable function. And as I said, the link function connects the random component with the systematic component. So some of the example of link function include a logit link. So it's essentially log mu I over 1 minus mu I. And there are also a number of other links depending on what kind of exponential distribution your random component follows. Okay, so that's the three components of generalized linear model. If you have any questions, leave in the comment below. Thank you.